Hi, I'm Ed Sperling. I'm the Editor-in-Chief of Semiconductor Engineering. I'm over at Cryptography Research Division of Rambus with Simon Blake Wilson, who's going to talk today about some of the problems that are going on in security, where we're starting to see some breakthroughs, where we're starting to see still seeing problems, and what the outlook will be as we go forward. It sounds like none of these by themselves will do the job. What do you need to do to really make a secure chip, a secure device, and add some security into almost everything that you use?
Sure. Yeah. So the emerging buzzword that you'll hear in this space is what's called an integrated root of trust. So this would something that would reside on a chip like the application processor and would work alongside, for example, things like TEEs that give software protection, but really give you something that's a foundational security component on the main chip that locks down a root of trust against all forms of attack.
So define integrated root of trust. What exactly is that from both functional standpoint as well as how do you work with this in a design?
Sure. Yeah, so let's talk about what the main properties of an integrated root of trust are. First of all, what is it? So I think it's really crucial to recognize that it's not just one thing, but it is a combination of primarily two aspects. So the first is an IP block on the chip. And when I say the chip, in the case of mobile, typically I mean the applications processor. Alongside that, what you have is what we would call, let's say, provisioning infrastructure. So, alongside that provisioning infrastructure, you're going to use it for example, for loading foundational root keys into the device as early as possible in the manufacture of the chip, right? So it's a block that resides on the chip that's set up to consume root keys that get provisioned during manufacture, and then use those keys to provide foundational security services. And those services could be helping, for example, the TEE or any generic application on the device after it's manufactured. So if we look at it from a functional perspective, what it's about is, well, loading root keys and then using those keys as a root of trust.
What's the power performance overhead on something like this?
So there's a number of different ways to look at that, and there's a number of different options you can choose. If you think about it from a gate count perspective, you're talking about sort of 1 to 300,000 gates on the device. From a power perspective, not typically material to the operation of the device in terms of its power profile. And then from a security perspective, and really crucial to understand is the idea that this has to really resist all attacks. So we talked about the TEE as being something designed as a pure software solution to prevent software attacks, and that's not enough going forward. The root of trust is something that can work on its own or in combination with the TEE, and if you like, leverage the protections that it has to make the combination impervious to hardware-based attacks.
And this becomes more difficult as you have always-on features on a chip, right? So something is always on, potentially can always be hacked.
Sure. Yeah, so if you like, what you're trying to do is to say, look, I need to have good security co-located on the chip, because we've talked about the problems of having discrete security elements. But what you want to do is to try to make the piece that you really protect in as bulletproof a way as possible, as small as possible, because otherwise you face an impossible problem of trying to provide great security for every component on the chip. It's just not a realistic goal. So if you like, those are the foundational pieces, right? What do we mean when we talk about an integrated root of trust? It's about a block that can consume keys and use them securely, and it's about an infrastructure that sits behind them, generates those keys, loads them, and retains the information that it needs to in order to do stuff after the fact, right? So these are keys that you load during a chip's manufacture, but you leverage them later, right? So you can use it to help secure the chip, but then when you put the chip into a device, you can leverage those keys you built in earlier to add whatever keys the device maker wants to. The same issue then for the application developer. Many of these applications need to consume keys to protect their information, you can now bootstrap or leverage these keys provisioned into the root of trust, to help the application establish the keys that it needs and protect them.
And one more piece of this, because it is integrated and inserted at the manufacturing stage, this really has to be part of the architectural design right up front, right?
Sure. One of the big maxims in security is always that you really need to consider security from day one in the design, right? It's 10 times harder to do good security if you you've designed your solution and you bolt on security at the end. Almost always a recipe for disaster. Much better to think about security from day one. Gives you a lot more options and a lot more flexibility to integrate it the way it should be done. Oftentimes saves you time and effort as well, because you're not stuck going back and redoing things once you address security later. So indeed, that's what you need to think about here. And really one of the fundamental principles here of an integrated root of trust is it's something that you put into the chip and you provision as early as possible in chip manufacturing. And once it's there, you can then leverage it to give you security benefits throughout the device's life cycle.
But another piece of this is everything's connected now on the Internet of Things. So you not only have to think about what's going on inside that chip, you also have to think about everything that comes in potentially a suspect, right?
Sure. Yeah, and I think there's aspects that you can leverage here, right? You can think about, for example, two devices talking to each other, whether it's two phones or the phone and the network, or the phone and your watch. And how do you secure that communication, right? One thing is obviously traditional approaches like antivirus, like scanning of incoming data, but also providing a secure pipe between those devices. And that's another area where an integrated root of trust can come in. If both your phone and your watch have an integrated root of trust through cloud-based security services, you can establish keys that are shared between those devices that they can use to protect their communications. So if it's my watch and it's set up to trust my phone, you can set up a secure pipe between them that they can rely on using this kind of technology.
Yeah.
If that's the set of properties that we aim for with an integrated root of trust, what does it look like in implementation? And actually, from a block diagram perspective, it's quite simple. So I'll try and show you that. So firstly, you have a set of OTP. Typically, we think of it as being private or protected one-time programmable memory that we're going to use to store some of the foundational keys. Connected to that, you have the main block of the root of trust. In our case, we call our component here Crypto Manager. And this is the component which includes a state machine, which will then control access to the keys that are programmed into OTP. And process commands which determine what can be done with the keys, who can access them, and so on. And then connected to the main crypto manager block and the state machine is what we call an extractor. And that's a terrible box diagram, but okay, hopefully it's clear. What comes out of the extractor? Well, firstly, you can connect it up to a set of feature bits, if you like. And secondly, you can think about the extractor spitting out keys. So how do these things get used? So we've talked so far about using it for security, but let's talk about using it for features for a second as well. What we see now is chips getting more and more complex, and chip makers with a desire to tape out fewer and fewer chips because of the cost. So what they've done in the past is make one chip with a number of features that can be turned on and off via OTP. And that's great, but as the number of features that you want to enable grows, you start to get limited by the amount of OTP you have. It's also something that where you can only turn the feature on and off once because of the nature of OTP. What you can do with this integrated root of trust now is instead program those features and hook them up to this extractor function. And then the root of trust will turn the feature on and off. And it can be done dynamically, meaning, for example, one feature might be debug of the chip. And you can provide a command that's secured with the keys manufactured into the chip, that could be used on a one-time basis to turn on the debug option. Once you've used that command, it can't be reused. So now the next time the chip boots up, the debug feature will revert to being turned off again. And you can think about this for any feature that you want to. Really quite a powerful concept for a chip maker. Firstly, it enables them to do fewer tape outs and save money that way. but it also enables potentially new business models for them where they can build features into the chip and then almost charge per use if they want to. The second kind of use case is around providing keys to applications. How would that work? Well, there's a couple of ways you can think about doing this. One of the options is to think about the root of trust as just being a key service. So you've got your bank's payment application running on your device. It needs to establish a key. Now, if you just send that key in the clear to the device, there's going to be a security problem. So what you can do instead is bootstrap the key that you've provisioned into the device during manufacture and use that key to now load the key that the bank wants. And then the bank's application can identify itself to the root of trust and provide the command with the encrypted key in, and provided the crypto manager state machine confirms it's the application that owns the key, it can either provide the key back to the application, or on behalf of the application, it can actually keep the key but use it to process transactions. So for example, sign your point of sale transaction on behalf of the device. And this way you get much stronger protection for that point of sale signing key than you would have through just a pure software mechanism. Storing it in the root of trust and provisioning it that way means that you can isolate that sensitive command and provide really robust state-of-the-art protection for it.
Simon Blake Wilson, thank you very much for a great explanation.
Thanks.